Fluorine is the most electronegative of all the elements, and it exists as a diatomic gas just as hydrogen does. And we'll see later on, as do oxygen and nitrogen and chlorine. If we want to make a model and the Lewis-Langmuir theory of this molecule F2, we notice that fluorine is in the 7th column, so it has 7 valence electrons, and F2 will have a total of 2 times 7 equals 14 electrons. So for us, we want to allocate the electrons in such a way that we can satisfy the octet rule for both fluorine atoms. The one way to do that is that we need to share 2 of the electrons between the fluorine atoms. So again, we see that 2 electrons shared between 2 atoms we call a single bond. So again, for F2, we need a single bond. The other 6 pairs of electrons are lone pairs. Again, we had mentioned that for the second row elements, nitrogen, oxygen, and fluorine, that when they have single bonds with themselves or with each other, that these tend to be very weak bonds. And the same thing is true with fluorine. So this fluorine bond has a very great tendency to break apart, and consequently F2 gas is extremely reactive. So in general, one does not encounter F2 intentionally as a pure gas because of this very high reactivity. Oxygen, the second most electronegative element, also exists as a diatomic molecule. So let's see if we can form the Lewis dot structure for O2, sometimes called dioxygen. Since oxygen is in the 6th column of the periodic table, it has 6 valence electrons. So we have a total of 12 electrons, and we have to allocate these in such a way that we can satisfy the octet rule for oxygen. And we know that we have to satisfy the octet rule because each of the cards for oxygen has a total of 8 holes that are surrounded by these gray shaded areas, which tell us that these are required to be filled. Now, if we do that and we try to form a molecule similar to the molecules that we've seen so far, such as for fluorine gas, F2, by forming a single bond, we run into a problem because we put 2 electrons to form a single bond between the 2 oxygens, and then we allocate the rest of the electrons. And we've used up all 12 electrons, but we still have 2 holes that are unfilled. That tells us that we have a problem. We have an invalid structure. So how can we solve the problem? Now, one way we can solve the problem is to realize that a species that's extremely important in biological systems is an ion called superoxide. So that is O2 with a -1 charge. So to model that, we would need 12 plus 1, or 13 electrons. So that would give us 1 extra electron, which we can put in here. And now we have a model of superoxide. So superoxide is good. For symmetry, let me put it there. So this is superoxide. Again, superoxide, having an odd number of electrons, is extremely reactive. And it's widely believed that ions such as superoxide and OH dot are important factors in the development of diseases. So now suppose we were to gain a second electron. So instead of being O2 -1, we had O2 -2. That would give us a total of 14 electrons. And if we put the 14th electron in here, we have now satisfied the octet rule for both of the oxygen atoms. Is this a real species? Yes, it is. This ion O2 2- is the peroxide ion. So it is a genuine and realistic ion, but this is not the way that oxygen exists as O2 gas. Because this is an ion, it has a -2 charge. So we need a way to allocate the 12 electrons among the 2 atoms in such a way that we satisfy the octet rule. So let's just show you the incorrect version for a second here, and we can think about how we can possibly solve the problem. Well, since we have two empty holes, what we'd like to be able to do is take some of the electrons over here, for example, that are lone pairs. Now, if we could share these two electrons, for example, with this oxygen atom, then these holes would be filled. These holes would be filled. We would have solved the problem. So let's show how we do that. But to do that, we need, in this system, specialized cards. So we'll show them in a second. Here we finally have the correct structure for O2 as a gas. Recall that we needed 12 electrons, but we needed to satisfy the octet rule for each of the oxygen atoms. So the way that we have to do it in the case of O2, and this is the first molecule for which we've seen it to be necessary, we need to share, instead of 2 electrons between the two oxygen atoms, we have to share 2 pairs. So in this case, when we share 2 pairs of electrons between 2 atoms, we call that a double bond. 2 electrons shared is a single bond. 2 electron pairs is a double bond. And then the rest of the electrons are allocated as lone pairs. So this seems to satisfy the Lewis-Langmuir theory. The question we might have is, does this correspond to reality? And it turns out, yes, it does. Double bonds exist. And double bonds have a couple of important features for us. One of the things is that a double bond in general will be stronger than a single bond. And we can measure thermochemically the bond strengths of compounds. So if you do this experimentally, we see that O2 is harder to break than it would be if it were a single bond. The other thing which is important about a double bond is that double bonds are shorter. Because the electrons help reduce the electrostatic repulsion of the positive charges of the nuclei, they're able to be closer together than they would be in a molecule where they're held together by a single bond. So we see that double bonds are both stronger and shorter than single bonds. We have various experimental techniques which actually allow us to tell how far apart the 2 nuclei in a diatomic molecule actually are. And we see that in the case of O2, this agrees with our prediction from the Lewis-Langmuir theory that we should have a double bond. Now, it will turn out later on that there are certain very important features of oxygen, of O2, that are not adequately explained by the Lewis-Langmuir theory. So it gets the idea of the double bond correct, the fact that it's stronger and shorter than a single bond. It also tells us that O2 exists as a diatomic molecule, so that agrees. But there are other features for which we need more advanced theories, such as the molecular orbital theory, to completely explain some of the very peculiar properties of O2. Nitrogen, N2, also exists as a diatomic gas. To model this particular molecule, we notice that each nitrogen atom has 5 valence electrons. So in a molecule of dinitrogen, N2, we need a total of 10 electrons. In this case, to satisfy the rules, we, instead of having 2 electrons, or even 4 electrons shared between the 2 nitrogen atoms, we have to share 6 3-electron pairs. So just as 1 pair is a single bond, 2 pairs shared is a double bond, 3 pairs shared is, as you might predict, a triple bond. So in N2 we have a nitrogen-nitrogen triple bond. Otherwise, so we see that as far as this nitrogen goes, it has 2, 4, 6, 8 electrons. This one has 2, 4, 6, 8. So these ones shared in between are counted both for this nitrogen and for that nitrogen. Now, as we had seen before with the oxygen case, that if a double bond is stronger than a single bond, we would predict correctly that a triple bond is even stronger than a double bond or a single bond. It is also shorter, so it's the nitrogen-nitrogen distance in N2 is very close. Now, because of this very, very strong triple bond, nitrogen as a gas is very unreactive. It makes up 80% of the atmosphere, but in general doesn't do that much. In fact, because of this lack of reactivity, Anton Lavoisier, the very important chemist, named it azote, meaning from Greek, not alive. And in fact, the Russian word for the name of the element nitrogen is actually azot, not alive. Now, we can break this bond to make nitrogen react, but to do that, we have to do it either at very high temperature, and where we can find that sort of temperature is in an internal combustion engine, for example, or it can be broken by lightning. So lightning is a very important source in breaking the triple bond of nitrogen and making the nitrogen atoms available for reactivity. Strangely enough, there are actually bacteria that have the ability to break this bond at essentially room temperature and atmospheric pressure. So without using lightning or very high heat, they can enzymatically break the nitrogen-nitrogen bond. So the particular bacteria that can do this are called Rhizobium, and they're generally found in the legumes. So legumes are a very important plant because up to a third of the energy of the plant is diverted to these particular bacteria, but in return, they make nitrogen compounds available as nutrition for the plant. Nutrition for the plant. Now, continuing with our theme of diatomics from the second row, we can go to C2 for carbon. Now, it turns out that carbon does not exist under any normal circumstances as a diatomic gas, as do fluorine, oxygen, and nitrogen. But we can form a very important diatomic ion. So this is C2, 2-. So each carbon contributes 4 valence electrons. So the 2 carbons together give us a total of 8. If we add 2 more electrons from the -2 charge, we have another 10 electron system. So this is C2, 2-, which goes by 2 different names. In inorganic chemistry, we call this ion carbide. In organic chemistry, we call it the acetylide ion. And the reasons for that will be clearer later in this video. But for the time being, we notice something else that's critical about how we think about things such as carbide. We notice that if I were simply to change the cards from nitrogen, these carbons to nitrogen, the model would look exactly the same as we had for N2. So systems that have the same number of atoms and the same number of valence electrons arranged the same way, we say are isoelectronic. So we notice that this carbide ion is isoelectronic with dinitrogen. And because of that, they have somewhat similar properties in that this ion is extremely stable and it's very, very difficult to break the triple bond. There is a very important organic compound which is found as a gas called acetylene. Its chemical formula is C2H2, and as we saw before, each carbon atom contributes 4 valence electrons. Each hydrogen contributes 1. So here we have a 10 electron system, but with 4 atoms. So we notice that the central structure looks very similar to carbide or acetylide ion, and very similar to dinitrogen. So in this case, we have a neutral compound where we satisfy the duet rule for each of the hydrogens on the outside. But to satisfy the octet rule for carbons, we need a triple bond in the center of the molecule. Acetylene is widely used combined with oxygen to form a very hot torch, so we have the oxyacetylene torch. So it's a flammable compound. While it's difficult to break the triple bond, once it does break, it generates a lot of energy. We can combine the elements of hydrogen, carbon, and nitrogen together to form a compound called hydrogen cyanide. This is a very, very toxic, poisonous gas. If we want to generate a Lewis dot structure for this particular molecule, we notice that each hydrogen contributes 1 electron, each carbon contributes 4, and the nitrogen contributes 5. So 1 plus 4 plus 5 gives us a total of 10 valence electrons that we have to allocate to satisfy the rules. And the only way that this is going to work is if we have a carbon-nitrogen triple bond. So this particular unit, if we just ignore the hydrogen atom here for a second, this carbon-nitrogen with a -1 charge is its own important ion called cyanide. So Cn-1 is a unit that is isoelectronic with N2 dinitrogen as well as the carbide ion. If we wish to model just the cyanide ion itself, Cn-, we need a total of 9 electrons for the carbon plus a nitrogen. Then since it has a -1 charge, we have to add 1 more electron. So again, we have another 10 electron system. So this is the cyanide ion, which is poisonous, but is also extremely useful in organic chemistry, as you'll learn, because it's what we call a nucleophile. So we can do some very interesting chemistry in organic synthesis by using ions with this particular structure. A very, very important diatomic gas is formed between carbon and oxygen, which goes by the name of carbon monoxide. Now each carbon contributes 4 electrons, the oxygen contributes 6, so we have yet another 10 electron system. So we notice that carbon monoxide is a poisonous gas. It is isoelectronic to the cyanide ion, which is a poisonous ion. So it may occur to us that there seems to be a very strong parallels between the reactivity of carbon monoxide and cyanide because they are both poisons. Now there's something else which is very closely related between these two species. Now normally when we have a diatomic molecule, we see these electrons being shared between the carbon and oxygen. In reality, it turns out that the electrons are not shared equally. Usually, when we have a diatomic molecule, the electrons are somewhat preferentially held, they're held a little tighter by the more electronegative element. Now, if we look at this, we might jump to the conclusion that we know that oxygen is the second most electronegative element that there is. So we might imagine that these 6 electrons, which are shared between the two, are held a little bit tighter to the oxygen. If that were true, that would give this side of the molecule a slight negative charge. It turns out that carbon monoxide is a very important exception to this rule. And for reasons which are not readily apparent within the Lewis-Langmuir theory, it turns out that the negative end of this molecule is actually at the carbon end. So much so that when carbon monoxide reacts, it will react with metals. Metals tend to be somewhat positive, they tend to be electropositive. So carbon monoxide will always bind at the carbon end as opposed to the oxygen end. One of the metals that carbon monoxide particularly likes to react with is iron. And we know that iron is found in the center of the molecule hemoglobin. We realize that carbon monoxide is a poison because it binds to the iron in hemoglobin and prevents it from carrying oxygen. So, you might imagine that cyanide does something very similar, and it does. In the cyanide molecule also, the carbon end is the negative end of the molecule. It also likes to bind to iron, but it doesn't bind to the iron of hemoglobin. It binds to the iron of a very similar structure called cytochrome C, which is involved in what we call the electron transport chain. So we can push the idea of this isoelectronic business and recognize that we see similarities, that two species are both poisons, and they're even poisons in very similar ways, but they're not exactly the same.